Good morning all. This is Dr. D. Khalandar Basha working as Associate Professor in Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the question bank related to Module 3, which is 8051 Microcontroller. First, illustrate following instructions of 8051 Microcontroller with detail. The first instruction is XCHD, which stands for exchange digit. Here, one of the argument is accumulator. The second one we are considering the memory, where the memory address we can write in any one register where I will take the values from 0 to 7. So if I have an instruction XCHD A comma at the rate of RI, the accumulator 4 bits, that is lower 4 bits, that is B0 to B3 of accumulator, will be exchanged with the memory location whose address is in RI register, where R can be 0 to 7. So in this memory location, the bit 0 from bit 3, these two datas will be exchanged. However, the upper 4 bits will be remains as it is. The next instruction is DA, which is decimal adjust. The contents of accumulator will be converted into packed BCD. So the output is packed BCD, where the packed BCD means each and every digit of the number of the BCD digit will be represented with 4 bits. So if we have the accumulator contents, which I am taking as 8 bits, each digit of BCD number requires 4 bits. So one of the digit is B0 to B3. The second digit is from B4 to B7. So first it will examine the lower 4 bits. If it is greater than 9, then add plus 6 to accumulator contents. If it is less than or equivalent to 9, no changes in the lower 4 bits. Once we examine the lower 4 bits, then it will examine the upper 4 bits, that is from bit 7 to bit 4. If it is greater than 9, we have to add plus 62 accumulator contents. If B7 to B4, if the data is less than or equivalent to 9, no change in the data. The next instruction is division operation. So for division operation, it is value should be provided only in accumulator and B register. The dividend we have to place in accumulator. The divisor we have to place in B register. For division operation, these registers A and B will not be separated by means of comma or space. Whereas for remaining instructions, comma will be there. For DIV, we have to write A, B. So here the dividend is accumulator and a remainder is B. After division operation, the quotient and the remainder will be placed in accumulator and B register respectively. We'll see the next question. Explain the following instructions of 8051 microcontroller with details. The first instruction is CJNE. C stands for compare, jump if not equal. So here the instruction will take the 3 operands, operand 1, operand 2. The third one is if the condition is satisfied, where the controller has to takes place the pointer from current location to the instruction which it has to execute. In this instruction, operand 1 will be compared with operand 2. After comparison, what for we are comparing is if it is not equal. That means if operand 1 is not equivalent to operand 2, then we will go to the address which we are specified. Otherwise, the subsequent instruction will be executed. If operand 1 is equivalent to operand 2, then it is going to execute the next instruction followed the CJNE instruction. Compare. After comparing operand 1 and operand 2, if they are not equal, jump to the relative address which you have specified. Otherwise, the instruction which is following the CJNE will be executed. The next instruction is RETI, which is written from an interrupt subroutine. So here, whenever any interrupt is occurred, for that particular interrupt, we have to execute interrupt subroutine. After executing the interrupt subroutine, the controller has to return to the main program. So when it has to indicate the end of this interrupt subroutine, how it will be specified for the microcontroller is in ISR, the last instruction will be always RETI, where it is zero operand instruction. So whenever the controller is encountered the RETI instruction, immediately it will transfer the control from ISR to some other activity like main program which are defined. Next one is mull instruction. For mull instruction also, the operand we have to specify in only accumulator and B register. The syntax of the instruction is mull AB. Here it is two operands, A and B will not be separated by any comma or space. We have to write as character. Here the 8-bit of the accumulator contents will be multiplied with the register. Whatever the 16-bit product which you are getting, that it will be there in accumulator and B register. The lower 8 bits will be in accumulator, the upper 8 bits will be in B register. Next, differentiate S jump, A jump, L jump instructions in 8051 microcontroller. So this JMP instruction is unconditional jump. So when any program is executing, whenever it encounters jump instruction, the control will be transferred to the address specified. This address may be lies in the upward direction or it may be located to downward locations. So anywhere it can transfer. How much distance we can have for this jump will vary the S jump or A jump or L jump. So whatever the address which you are specifying, what is the size of that particular address space? Whether it is 8 bits or 11 bits or 16 bits, depending upon that, we are going to have 3 unconditional jump instructions. They are long jump, absolute jump and short jump. The syntax of the instruction for L jump is L jump, the address whichever you are going to provide, that is a 16-bit wide. Whereas second instruction which is A jump, that is absolute jump, here the address length is 11 bits. The third one is S jump. It is also unconditional short jump, where the displacement we can have 8-bit wide. So address space we are going to have 8 bits. 7 bits we can represent for upward, 7 bits we can represent for downwards. The next instruction is compare the functionality of move, move-C and move-X instructions of 8051 microcontroller. The move instruction, it is for moving the data from one location to another location. Either it can be a register to memory location or memory location to memory location or memory to memory. So where the data is residing, based upon that and what kind of data we are transferring, we have 3 kinds of move instructions: move, move-C and move-X. So the move instruction, it is for the data, if it is related to, or if it is residing inside the microcontroller, either it may be registers or memory location. The data, if it is referring to on chip of the 8051 microcontroller, we are going to use move instruction. The next instruction is move C, where C stands for whatever the data which we are transferring, it is related to code information. The next one is move X instruction. This X indicates we are transferring a data transaction with external memory. Either from the external memory to microcontroller or microcontroller to external memory, we are going to use move X instruction. So if I have move X A comma at the rate of DPTR. So now the data we are having in memory, that memory address we are having in DPTR, that contents will be loaded into accumulator. So this is the data transfer from the external memory to accumulator. Similarly, if you want to move to the external memory, reverse fashion. Move X at the rate of DPTR comma A. Next, list and explain rotate instructions in 8051 microcontroller. In 8051 microcontroller, total we have 4 rotate instructions. One is rotating towards left side without carry. The second one is with carry. Similarly, for rotating towards right without carry and with carry. Based upon that, total we have 4 instructions: RL, RLC, and RR and RRC. The first one is RL instruction, which is rotate accumulator left. So here the accumulator contents which are B0 to B7, 8 bits wise. These contents will be rotated towards left side without carry. So when you are rotated, B1 will sit in B0 position, B2 will sit in B1 position. The previous MSB is B7, that will sit in B6 position. So what about this LSBs? This B0 bit will be moved into MSB position, as well as this will be moved to carry. This is rotate accumulator towards right side. If you want left, now we'll see RL, which is rotate left. So now the accumulator content is B0 to B7. When you rotate these contents towards left side, B7 will be copied into carry flag. B6 will be sit into B7 position. B0 will sit in B1 position. The LSB is the B7 value. This is RL, R. The next instruction is RLC and RRC. The RLC instruction, rotate left with carry. So here the accumulator content is B0 to B7. We are going to rotate towards left side along with the carry flag. Whatever the B7 bit MSB value is there, that it is going to sit in carry flag. The previous carry will sit in the B0 position. However, remaining bits B6 will sit in MSB position, B0 will sit in B1 position, LSB will be occupied with carry flag. This is rotate left with carry. The next instruction is RRC, which is rotate right with carry. So in the rotate right with carry, assume the accumulator content is from B0 to B7. When you rotate these contents towards right side, B0 will be copied into carry flag. B1 will be placed in LSB position. B7 will be copied into B6 position. Here, the MSB will be occupied with the previous carry. Before executing this instruction, whatever the carry is there, that will be set in MSB position. Next, outline 8051 program to convert BCD number available in accumulator into 2 ASCII numbers and save them in the internal memory location 48H and 49H. So here we are given with a packed BCD number sub XY. This we want to convert into ASCII digits. One of the data we are going to load in 48H, the second one is in 49H. So for converting this into ASCII, the XY data, first it has to, we will consider this one as a packed BCD number. This packed BCD number will be converted into two 8-bit data, which you are going to consider as unpacked BCD. Once we got unpacked BCD at 3030, then we will get the ASCII digit of X and ASCII digit of Y. Now, if you observe here, in this data, the upper 4 bits are cleared, the lower 4 bits are retained as this. Whereas for X, the lower 4 bits are cleared and X, which is in the upper 4 bits, that is moved to lower 4 bits. So for this, the program will start at 8000 location. Whatever the BCD number which we want to convert into ASCII, that will be moved into accumulator by using move A, BCD number. As we want to perform these two operations, a backup copy we are going to be loaded into R2 register by using the instruction move R2, A. For fetching only the lower 4 bits and with 0FH. When you AND with any bit with 0, it is going to retain 0. If we AND with 1, the same digit we are going to have. Suppose if I have B7, B6, B5, B4, B3, B2, B1, B0. When you are ANDing with 0F, 0F means in the hexadecimal binary equivalent is 0000. For F, the binary equivalent is 111. Any bit AND with 1 will return the same data. So B1, B2, B3 will be written as this. If any bit AND with 0, it is going to clear the upper 4 bits. So now upper 4 bits are cleared, the lower 4 bits are retained when you use ANL instruction. Next, R. Either you can go for add instruction, otherwise you can go for R instruction. Both are valid. When you add this with 30H 0011 0000, you will get B0 ORed with, this is AND operation, this is OR operation. B0, any bit ORed with 0 will get the same bit. Any bit ORed with 1 will get 1 1. If you ORed with 0, previous data will get. So this is the ASCII equivalent. Now whatever the ASCII value which we got, that we are moving into 48H. So this 0Y we have moved into 48H memory location. Now our objective is we want to get for X also. So the second copy we are having in R2 register, that will copy again into accumulator. Then we go for ANDing with F0. When you AND A0 contents, which is 8 bits, B7, B6, B5, B4, B3, B2, B1, B0. When you AND with F0, F means 1, 1, 1, 1, 0 means 0, 0, 0, 0. Any bit AND with 0 will give 0 only. If any bit AND with 1, the same bit it is going to return. Now this data, we want to exchange the lower 4 bits with upper 4 bits. For that, we can use swap operation. When you swap, the lower 4 bits will be exchanged with the upper 4 bits. When you go for swap operation, here this will get B7, B6, B5, B4, whereas upper 4 bits are 0, 0, 0. Now we are converted into unpacked BCD for upper 4 bits. Then for getting into ASCII, and with odd with 30H 11 0, 0, 0, 0. When you are any bit with 0, it is going to give the same bit. So B4, B5, B6, B7. If any bit odd with 1, you get 1 only. If any bit odd with 0, this data only will be sent. Now this is ASCII equivalent for 1. So accumulator contents will be moved to the target location, which is 49H. Then we will terminate the program by using halt instruction. Demonstrate using 8051 to move an array of data between two external memory blocks. So let us consider this is some external memory. Here we have a block of data. This we want to copy into this memory location. Directly external memory to external memory is not possible. So what we will do is, first this data will be placed into the internal memory of 8051. Once it is copied into internal memory, then we are going to be load that one into external memory. Whenever the data is copied into the internal memory, move will be used. If it is from external memory or to external memory, move X will be used. How many memory locations we want to move, that will be loaded into R7 register. From which address the data has to be loaded, that from address will be loaded into DPTR. Next, the internal memory address will be loaded into R1. So first, external memory data will be copied into accumulator by using MOVX instruction, accumulator from the external memory. Now, whatever the accumulator content is there, that will be copied into the internal memory. So for that, move at the rate of R1. This will refers to the internal memory. Accumulator contents will be copied into that memory location. Next, for pointing to the next address, we have to increment the address pointer which is in DPTR for external memory. For internal memory, R1. So we go for incrementing DPTR R1. Now it will point to the next memory location. As one memory transaction is done, number of memory locations which we are going to transfer will be reduced by 1. If it is non-zero, then go for next iteration. Once the count is 0, we can come out of the loop. So for that, the count which is in R7, this will be decremented. If R7 is non-zero, go to loop 1. So this loop 1 will be iterated to copy external memory data to internal memory. Our objective is from external to external. The next task we are having is from internal to external we have to transfer. So again we will load R7 with the number of memory locations, R1 internal memory, DPTR the target address. Now we will fetch the data from the internal memory to accumulator by using move A at the rate of R1. Now this accumulator contents will be moved to the external memory by using move X at the rate of DPTR comma A. Next, for pointing to the next memory location, increment DPTR, increment R1 register. As one memory location is copied, decrement R7 register. If it is non-zero, go to loop. So this loop 2 will copy the data from internal memory to the external memory. Once all the memory locations are copied, then we can terminate the program by using HLT instruction. Next is show the use of push instruction to put the number 82H in RAM location 34H to 37H. Also list out the same program without using push instruction. So here push, it is mainly used for stack operations. So we assume the stack pointer is pointing to 33 location. Start of the program is at 8000 location. Stack pointer is loaded with 34H. The data which we are copied into that memory location is loaded into one of the memory location which is 50H in this example. How many memory locations we are copying? 34, 35, 36, 37. So that means it is 4 memory locations. So that will be loaded into R7. So as stack pointer is pointing to 34H, push 50H. Now 50 will be loaded into the top of the stack. Next, as one data transaction is done, we will decrement R7. If it is non-zero, go to loop 1. So this 2 instruction will be executed for 4 times. where to load the 50H memory location data into that memory location starting from 34 to 37. Once all the data is copied, this condition fails, it will come out of the loop where we can terminate the program by using HLT instruction. The same program we will see without using push instruction. R7, 04H. The starting address we are going to be loaded into R1, 34H. The immediate data we are going to be loaded into the internal memory by using move at the rate of R1, 82H. Then we have to increment R1 for pointing to the next memory location. Decrement for each transaction the count in R7. If it is non-zero, go to loop 1. So these three instructions are used for transfer the data or load the data into 4 memory locations. Then we can terminate the program by using HLT instruction. The next one is demonstrate the program in 8051 to count number of bits available in a byte available in external memory 1000H, store bit count in internal RAM 60H. So here a byte means we are going to have 8 bits. The objective is we want to find how many bits are 0 in this data. So for this purpose, either we will rotate the contents either towards the right side or left side by 1 bit. When you rotate these contents, then the bit for right direction, that is LSB bit, will be moved into carry flag. If it is for left, MSB will be moved to carry flag. By checking the carry flag, if carry flag is equivalent to 0, increment the count. If carry is equivalent to 1, don't change the count. Once all the count is evaluated, we have to load the count into internal memory at the 60H. Now you see the program. As we want to check 8 bits, R7 will be loaded with 08H. The external memory address is pointed by DPTR, so load the 1000H into DPTR register. Then fetch the external memory data into the accumulator by using move X accumulator comma at rate of DPTR. The internal memory address, that is 60H, we are going to be loaded into R0. We will clear the R0. Whenever any bit is 0, then we go for incrementing that particular memory content. Here, rotate these contents towards left side or right side, all are valid. So here I can use RR instruction or RRC instruction or RL instruction or RLC instruction. Any instructions we can use. Once you rotate it towards left side or right side with carry or without carry, then we will examine carry. So what is the objective? We want to find out 0. But if carry is equivalent to 1, nothing to be done, go for next iteration. If a particular bit is equivalent to 0, carry flag will become 0. This condition fails. Subsequent instruction will be executed, where we are going to increment the memory location, which is 60H, which is loaded into R0 register. After checking 1 bit, we have to check total 8 bits. So decrement R7 register. If R7 is non-zero, go to loop 2. So this loop 2 will be iterated for 8 times. Once all the 8 bits are done, DJNZ will terminate the loop. Then we can stop the program by using HLT instruction. Illustrate how to find the average of 5 numbers. Store the result in 55H in 8051 microcontroller. Here the objective is we have to find out the average of 8 8-bit numbers. And the result we have to store in 55H. So first we will fetch 1 data, assuming the data is residing from 30 to 34H, because 5 data we are having. These 5 data we have to add. So this data we will load into accumulator every time. We will add these contents. Then we will load that one into the R2 register. Later we can move into the memory location. 30H address of the memory. 5 data, so count we are going to be loaded into R1 register. R2 initial sum we are going to be load as 0. Accumulator is cleared by using move accumulator comma 00h. Fetch the first data at 30h location by using the instruction move a comma at the rate of R0, where R0 will consist of the memory location which is 30h. Then add these contents R2 which is cleared a previous added data with accumulator. After addition, the result will be there in accumulator. So A is assigned with A plus R2. So this will be again reload back into R2 register. Then for accessing the next memory location, increment R0. As one data we have added, decrement R1 register. If it is non-zero, go to loop. Next, once all the 5 elements are added, we have to find the average. So the sum which is in R0 register will be divided by B register, which is equivalent to 5. So load the number of elements into B register. The address where we have to store that we are going to be loaded into R4 register. The sum which is in R2 register that will be load back into accumulator, because for division the syntax of the instruction is divb. The dividend which is sum we have to load into accumulator. B is divider which is equivalent to 5. Then give div a. So after division, the quotient will be there in accumulator. So that we are going to be loaded into the target memory location, which is nothing but 55H. Then we can terminate the program by using HLT instruction. Show the ALP for smallest number in a given array using 8051 microcontroller. Write a program to compute the sum of n numbers and save the sum at 70H. So here n value will be passed. We are going to add the elements 1 plus 2 plus 3 plus 4 like this until n. The sum again we have to load into 70H location. So here this program will be loaded at 000. Constant n is loaded with 15. So we need to find out from 1 plus 2 plus 3 until 15. Initialize R0, that is initial sum as 0. Clear accumulator also. We want to start from 1. So increment R0. This value add for accumulator. As sum is there in accumulator, or the number of data which we are having, we have to reach until 15. So R0 will be compared with n value. If they are not equal, go to loop 1. So this loop will be iterated for n times. Once n times is done, the sum which is in accumulator that will be loaded into target location, that is 70H. Then we can terminate the program by using HLT instruction. Describe the register set of 8051 microcontroller with examples. So in the register set, we have to consider what are the various registers are having in 8051 microcontroller. So we have a register bank 0, where each bank is consist of registers R0 to R7. So these 8 registers are present in register bank 0. Similarly, R0 to R7, that is 8-bit registers, will be present in register bank 1. R0 to R7, which are 8-bit in number, will be stored or referred as register bank 2. Similarly, from R0 to R7, 8 more registers are also placed in register bank 3. So this register bank 1, bank 2, bank 3, these 4 banks will consist of 8 8-bit registers. Apart from that, we have special function registers for interrupts, interrupt enable, interrupt priority. For serial communication, PCON, SBUF, SCON registers. For timer usage, TCON, TMOD, TL0, TH0, TL1, TH1. Apart from this, we are having a DPTR register which is loading the external memory, program counter, which will contain the current memory location which code has to execute by the controller. Accumulator and B, which will process the data to ALU. Program status word, which will keep track of all the flags as well as which register bank we have to select, that we can program by using PSW. For each port, we have 4 registers: port 0, port 1, port 2, and port 3. Explain internal architecture of 8051 microcontroller with the need diagram. Already we have discussed the registers. Left out is we have an internal memory. In this internal memory, 32 locations are reserved for registers. On the top of that, 16 we are going to have bit addressable area. Next we have special functions. On the top we are going to have internal RAM locations. Internal it is consist of 4K RAM, and these SFRs are these blocks. So this is 128 bytes. Out of 128 bytes, 32 we are having here. 16 will be there in the bit addressable. On the top we have byte addressable area. This system timing, system interrupt, timers, data buffers, memory control will have one control logic. And 8051 will consist of 4 ports: port 0, port 1, port 2, port 3. Few ports are multiplexed. Few ports will be worked as only IO purpose. Port 0 will consist for providing the address on A0 to A7 lines. Port 2 will have the address and data lines on AD0 to A8 to A15. Data we are going to have in AD0 to AD7, that is on port 0. Outline the addressing modes of 8051 microcontroller with examples. So the way with the data sources or destination operands are specified in the mnemonics that move the data determines the addressing mode. In 8051 microcontroller, we have 6 addressing modes. Immediate addressing mode. Immediate addressing mode means the data should be reside in the instruction itself. Direct addressing mode, if the memory address, if you are specifying in the instruction, then you will call as direct addressing mode. Register addressing mode, if the data is present in any one of the register, then it is register addressing mode. Register indirect addressing mode, where the data is present in the memory. This memory address we are going to be loaded into some registers that we are going to place here. We will call this one as register indirect addressing mode. Indexed addressing mode, where the offset or memory address will be calculated by addition of accumulator and program counter. It is mainly used for accessing the data from or to code memory. Implied addressing mode. Implied addressing mode means no need to specify where the operand it is. By using the instruction, automatically the data will be fetched from that particular registers. So RLA, which is implicit operand, where rotate left only the accumulator contents. The accumulator contents will be rotated towards left side. Next, explain the significance of bit addressable features of 8051 microcontroller. Show the various components of internal memory. In 8051 microcontroller, we are going to have 128 bytes of RAM, out of which 8 registers are there for bank 0, 8 in bank 1, 8 in bank 2, 8 in bank 3. Then we'll have 16 memory locations which are bit addressable. Whenever we are referring to a memory, how the data you are accessing, either we are taking the data to or from 8-bit size or only 1 bit, that will differ bit addressable or byte addressable. In these 16 memory locations, that is from 20 to 2F, we can access only one memory at a time, or we can access the entire 8 bits at a time. So that's why this area we can write as bit addressable as well as byte addressable. On the top of that, that is from 30 to 7F, we are going to have the general purpose RAM, where this one is only byte addressable. Elaborate the significance of the following signals of 8051 microcontroller. PSEN bar. So in 8051 microcontroller, we are having ROM. Whenever we want to load the program into RAM, this pin, which is program store enable, should be low. When PSEN bar is low, then the data can be copied into code memory. Initially, when we are writing the data into ROM, PSEN bar will be made 0. Once the data is loaded, which is code is loaded into the microcontroller, PSEN bar usually will be connected to VCC so that no further write operations will be takes place for ROM. Next, XTAL1 and XTAL2. So a crystal oscillator for providing the clock pulses, we are going to connect this one in the 8051 microcontroller for the pins XTAL1 and XTAL. This crystal oscillator will generate a frequency of 11.0592 MHz, which are needed for providing the clock pulses of 8051 microcontroller. Next, T0, T1. These are the two interrupt signals which are generated by timer 0 and timer 1 respectively. Describe the special features of special function registers of 8051 microcontroller. By having the registers are accumulator, B register, program counter. Program counter will load the address of the next instruction to be executed by the microcontroller. DPTR either we can access as 16-bit or 8-bit. If you are using as 8-bit, DPL and DPH. Stack pointer, SP, which will point the top of the stack always. PSW, which is program status word, which is going to contain flags and which register bank we have to select. Next, we have port 0, port 1, port 2, port 3 to have the data transaction with IO device, either through IO device or from the IO device. Next, for timers, timer 0 count will be specified in TH0 and TL0. For timer 1, TH1 and TL1. For configuring the timer, we have timer control. For selection mode of the timers, we use T mode. SBUF for serial data transfer, the data will be loaded into SBUF. For serial port control, we have SCON register. PCON it is for power control. For interrupts, for enabling the interrupt IEE register. For giving the priority, we have IP register. Show the PSW register format of 8051 microcontroller. So the PSW format is shown in figure. Pin stands for the parity flag. This will specify how many number of ones are there in your data. OV stands for overflow flag. So whenever the result size is bigger than the target, then it is going to give as 1. RS0, RS1, this is for register bank selection. When you configure 00, register bank will be selected, bank 0 will be selected, 01 bank 1, 10 bank 2, 11 bank 3 will be selected. F0, it is user defined flag, no significance. Next, AC, which is auxiliary carry. If any carry is generated or any borrow is taken, any carry or any borrow is generated in the lower nibble, that is lower 4 bits, then auxiliary carry will be generated. The last bit, which is carry flag, if any carry is generated or any borrow is taken at the MSB position, then the carry flag will be set to 1. If there is no carry, no borrow in the MS position, carry flag is equivalent to 0. Outline ALP to identify even or odd numbers in a given array in 8051 microcontroller. So for finding out whether the given number is even or odd, rotate the contents towards right side by 1 bit. Once this content, that particular bit will be moved to carry flag. If carry flag is equivalent to 0, we'll consider this one as a even number. If carry flag is equivalent to 1, we'll consider the data as odd. So the number for which we want to find out whether it is even or odd, move into accumulator. Rotate these contents either through carry or without carry. Anything is valid. Accumulator contents will be rotated towards right side by 1 bit. Then examine carry flag. If it is carry flag, go to the odd label where we are going to write accumulator as 1. If it is condition phase, that is, if carry flag is equal to 0, the subsequent instruction. So accumulator will be cleared. Then we will go to even where we don't have any instructions. You can halt. You can stop the program. So thank you. In this session, we have discussed the questions related to module 3, which is on 8051 microcontroller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.